A circuit board removed from a failed device sits on the bench. The enclosure came off in 4 screws. The board itself is clean. No burn marks, no corrosion, no physical trauma visible at this magnification. That cleanliness is the first thing to hold in mind because it means the surface is not telling the truth about what happened here. We are going to take this board apart layer by layer, and the deepest layer will not be what the surface implies. This is not a story about a board that broke. It is a story about geometry, specifically about how the geometry of one small component made the rest of the board irrelevant. The enclosure first, then the connectors, then the passive components, then the processor, then the memory, then the storage, and finally the firmware chip, soldered flush against the substrate with no socket beneath it, the layer where the teardown ends and the disposal begins. The outer shell came off cleanly. 4 standard fastener points, all of them free without protest. The enclosure on most consumer and light commercial circuit board assemblies is fastened mechanically. Screws, clips, snap-fit tabs. These fastener patterns are standardized, and in many cases they trace their geometry to manufacturing conventions that were established well before the cost reduction era that later reshaped everything deeper in the stack. The enclosure exists to protect the board from its environment: dust, contact, mechanical shock. Its removability is a legacy of an era when servicing was assumed as part of the product lifecycle, when the person who would eventually open this device was a considered participant in the design conversation. The teardown suggests this has nothing to do with the manufacturer's current repair philosophy and everything to do with when the enclosure geometry was locked in. The surface is reachable because the surface was standardized before the pressure arrived to make things unreachable. This board shows no sign that the enclosure was ever the cause of anything. The connectors along the board's edge come next. Power input, data ports, peripheral interfaces. These are through-hole or surface-mounted components with bodies large enough to be grasped and in most cases desoldered with standard iron and wick technique. Their failure modes are well documented in service literature. Mechanical fatigue at the solder joint from repeated insertion cycles, oxidation on contact surfaces in humid environments, physical breakage of the retention tab under stress. None of these are present here. The reason these connectors are accessible has nothing to do with a manufacturer's commitment to repairability. Connectors are large because the mating plug is large. The physical constraint of the hand that plugs a cable into this device, or the industrial connector that interfaces with this board in its operating environment, sets a minimum size for these components that no cost reduction pressure has been able to dissolve. That constraint has kept them reachable. They are, as a result, the layer of the board with the most active repair ecosystem. Replacement parts exist in distribution. The technique is in the documented toolkit. The cost is low enough to make sense. Under magnification, the solder joints on these connectors are intact. The contact surfaces are clean. This layer did not fail. Moving inward, the teardown reaches the passive component population: capacitors, resistors, inductors, and the discrete components of the power regulation circuit. On this board, these are predominantly surface mount components in mid-range packages, not the smallest available, but not through-hole either. Capacitor failure is the most common cause of board-level failure in this class of device, and it announces itself visibly: swelling at the case, electrolyte residue on the board surface, or a measurable shift in equivalent series resistance that a basic meter will catch. The passive components on this board are measured. The values are within tolerance. The power regulation section is functional. Physics is, incidentally, what keeps these components visible and replaceable. A capacitor's capacitance is determined partly by the physical dimensions of its plates and the distance between them. Below a certain size, the component cannot provide the capacitance value the circuit requires. That floor, the floor set by the physics of what a capacitor is the same floor that keeps these components at a scale where the teardown can see them, measure them, and if necessary, replace them. The fault is not here. The largest single component on the board is the main processor. It is mounted in a package large enough to require a substantial solder footprint for thermal reasons. The processor generates heat, and heat requires surface area, and surface area is the accidental ally of the repair technician. This is the one layer of the board where the thermal physics of silicon briefly align with the interest of the person trying to fix the device. The processor can be identified. Its part number is readable under the microscope. Its datasheet is locatable. If this component had failed, a replacement would be expensive and the rework would require a hot air rework station. But the operation is documented, the parts exist in distribution, and a competent board-level repair shop has the tools to attempt it. The processor is not socketed on this board. That practice largely ended as a cost reduction measure in consumer products, but its package is at minimum accessible. The teardown identifies no fault here. The solder joints show no cold joint signature. The component did not cause this failure. The board is still clean, still functional at every layer the teardown has reached, and the fault has still not been located. Volatile memory sits close to the processor, either in discrete packages or in a stack mounted directly above the processor die. In either configuration, the memory is surface mounted without a socket. Socketed memory, once standard in consumer computing products, was eliminated in mobile and embedded designs in the early 2010s and has continued its retreat from mainstream consumer products throughout the following decade. The reason is stated openly in the device's own marketing materials. Thin. A socket adds height. Height contradicts the target device profile. The consequence is soldered memory, and the consequence of soldered memory is that if it fails, the repair becomes difficult and expensive. Still possible at a shop with the right tools, but no longer within reach of the general service ecosystem. This board's memory packages show no signs of failure. The teardown continues inward, discarding diagnostic layers one by one. The storage component on this board is a surface mount package with contacts only on its underside. Unlike the memory, storage on this class of device carries firmware alongside data, and the distinction matters for repairability. Replacing a failed storage chip requires not only the physical operation of removing and reflowing the package, but also writing the correct firmware image to the replacement component before or during installation. That firmware may be publicly available, or it may not be. The company's own policies on firmware distribution vary, and independent repair documentation, where it exists at all, is the work of communities rather than manufacturers. The package itself is a ball grid array format. The contacts are beneath the body of the chip, invisible from above, accessible only by lifting the entire component off the surface it is joined to. A service shop without X-ray imaging capability is, at this layer, working from inference rather than observation. The board's storage chip is identified, its package confirmed. And here, at last, the teardown reaches the layer that failed. Beneath the storage layer sits a smaller chip. It is a firmware component, the chip that holds the initialization code the processor runs before any other software loads. On this board, it is also a ball grid array package, contact balls arrayed across its underside, no socket, soldered flush to the substrate. A ball grid array chip sits on its contacts the way a waffle sits on a griddle. The connection surface is entirely underneath, invisible from above, accessible only by lifting the whole component off the surface it is joined to. You cannot inspect the joint from the side. You cannot add solder from above. You can only heat the entire interface uniformly and hope the component releases cleanly, which it will do once under ideal conditions before the pads on the board begin to show the fatigue that repeated thermal cycling introduces. The contact balls on the underside of this chip, each one a sphere of solder alloy, are, at the scale the teardown is working, roughly the diameter of a human hair in cross-section. There are dozens to hundreds of them depending on the chip's pin count, arrayed in a grid that is only legible under X-ray. The teardown cannot count them directly. Replacing this chip requires a hot air rework station, a stencil, a microscope, and an X-ray system to verify the result. A skilled operator at a well-equipped shop can perform this operation. The teardown's claim is about the modal service shop, the one most likely to receive this board, not about the outer limit of what is technically possible. The physical requirements are fixed: controlled heat, accurate stenciling, and X-ray verification. The distribution of shops meeting those requirements is not uniform. Most of the service infrastructure that handles consumer and light commercial devices does not include X-ray imaging, because the business case for that equipment is not built around a category of board that was assumed to be disposable when it was designed. Current distributor pricing for this component, as reflected in publicly accessible component databases, sits roughly 25% above where it was before supply chain pressures reorganized the component market. The company's own authorized distributors reflect this in current pricing. The repair, if attempted, costs more than the board is worth in the device's current market. The board will not be repaired. The firmware chip is in a ball grid array package because it was cost optimized for a high volume manufacturing line where this package placement is routine. The choice was not made with repair in mind. It was made with assembly yield, component density, and board real estate in mind, and it was the correct choice for all of those purposes. The side effect, that the component now sits beyond the practical reach of most service operations, was not weighed against those factors, or was weighed and accepted. The teardown cannot determine which. What the teardown can state is that this chip, which is roughly the size of a thumbnail and holds a small quantity of initialization code, is the reason the entire assembly is destined for disposal. The board is not being discarded because most of it failed. It is being discarded because the one component that did fail is the one whose geometry places it at the intersection of two trajectories that have been running in parallel for 30 years. The miniaturization curve that removed its socket, and the cost structure of the repair industry that never acquired the equipment to reach it. The constraint that made this chip small is the same constraint that made it unreachable. Those are not two separate facts. They are the same fact stated in different units. Before the anatomy reaches its reading, three things the dissection cannot settle. First, the teardown cannot establish whether the firmware chip's failure was a manufacturing defect, a wear-out mechanism, or a corruption event caused by something else on the board that is since resolved. The chip is identified as the failed component by functional inference. The board initializes to a certain point and stops, but the root cause within the chip is not accessible without opening the package itself, which ends the repair and the diagnostic simultaneously. Second, the claim that a replacement chip is not practically available through standard service channels rests on current distributor pricing and publicly accessible component database listings. The teardown cannot confirm that no source exists in all markets, only that the sources reflected in standard databases present a price point that alters the repair calculation significantly. Third, the assertion that ball grid array rework is beyond the capability of most service shops is a generalization. There are independent technicians and specialized board-level repair operations that perform this work routinely. The physical limits are fixed. The distribution of shops that can meet those limits is not. What the dissection settles is narrower than what the dissection suggests. This board, this chip, this geometry, and this price point combine to produce a discard outcome that has nothing to do with the condition of every other layer on the board. The board on the bench is, in the anatomist's plain assessment, a document. It records 30 years of decisions made by people who were not thinking about the technician who would eventually open it. The enclosure was standardized before the cost pressure arrived. The processor stayed large because heat physics required it. The memory lost its socket because the device got thin. The firmware chip was packaged in a ball grid array format because the assembly line was optimized for density. No single decision was unreasonable. The aggregate of all of them is a board that can be opened, examined cut by cut, found to be mostly intact, and still not fixed, because the one layer that matters is the one layer that geometry placed beyond reach. The miniaturization that made this device possible is the same miniaturization that made this device unserviceable. The constraint is in the chip. It has been there since the component was placed. Every layer above the failure was reachable, and every layer above the failure was fine. There is another board on the bench. Name the object you want to open next, the one whose surface you think you understand, and whose deepest layer you are less certain about. If this dissection was useful, subscribe and turn on notifications. The next object goes on the table in the next video.